Hi, welcome back. This is part 6 of the tutorial on drawing the Lewis dot structure, and this one we're going to make use of the Lewis dot structure and combined with the understanding in the previous section of the tutorial on the shape, the understanding of electron density, the understanding of negatively charged electrons to predict the shape of each molecule. Now, I want you to understand that this is not rocket science. Is very easy to understand. You just have to be patient and look at the model on your hands. Okay. So what I want you to do right now is get some pen and pencils ready. Okay, because we're going to make use of these pen and pencils to get simple models and make you understand and enjoy this learning on the structure. Now, in the previous part of the tutorial, we talked about counting electron densities, understanding that electrons would naturally repel each other because of the negatively charged nature. Okay, so you understand how carbon dioxide is actually a linear structure because they have to minimize repulsion between the electron densities. You understand that methane is tetrahedral because it would naturally try to minimize repulsion, so it will be a three-dimensional structure. BH3 would be a trigonal planar. Okay, each angle is 120 degrees to minimize the repulsion. Now let's get into the detail about the shapes. Okay, now we talked about electron densities in the last part. What else can we learn here? Okay, now there are two terms I want to introduce to you. Okay, let me write down on the board. There's one term called the electron geometry. Okay, that's the first term. The other term is called the molecular geometry. Okay, we have these two terms here, molecular geometry and electron geometry. Now, I would consider to understand I would help you to understand electron geometry first, and then the molecular geometry. This is the order. Okay, so first, I hope you understand the concept of electron densities. It is just basically a group of electrons regardless of the quantity. Okay, like here we have 4 electron densities around the oxygen. A single bond would be considered as an electron density. A lone pair electrons would be considered as a single electron density. So therefore we have 4 electron densities around this oxygen. On the other hand, here for carbon dioxide, for the double bond is considered as a single electron density because as a single electron density because the 4 electrons in the double bond are physically together. Okay, so therefore we have 2 electron densities around carbon. Next up, okay, what is electron geometry? Now, when we talk about electron geometry, we would just focus on the distribution of the electrons, the orientation of the electron densities. Okay, so we put our focus on the electron densities. So in this case, carbon dioxide, we talked about in the last part, we talk about this is the structure, this is the shape. Because in this shape, this is 180 degrees, this is 180 degrees, so the repulsion will be the minimum in this orientation. So this is how we know that for carbon dioxide, it is in a linear structure. Okay, so let me write it down. For carbon dioxide, it is linear. Okay, now, what happened? What happened if you have a diatomic molecule like N2? Okay, so in this case, so which one will be considered as a central atom? Well, it doesn't matter. You can pick this nitrogen or this nitrogen. So let's pick this nitrogen and let's count the electron densities. 1, 2. Okay, so 2 electron densities. How can they be minimized? Now, I'm going to use the 2 different colors. This marker will be considered as the triple bond right here. Okay, the cap here could be considered as the nitrogen atom. Now, the red marker will be considered as the lone pair electrons right there. Okay, so there are 2 electron densities around the nitrogen. Okay, so my fifth will be the nitrogen atom here. So this is the best orientation to minimize the repulsion. lone pair electrons right here, triple bond right there. This angle is 180 degrees. That's the minimum repulsion, okay? The greatest distance to minimize repulsion. So therefore, this will be considered as linear, okay? For the this will be considered as linear for the electron geometry. Now let me color code the naming just so that you don't get confused. So the green color would be the electron geometry, and later on when we talk about the molecular geometry, I'm going to use blue marker to label them. Now let's consider this one, okay? So so again, I'm going to use this for the same electron densities like the single bond. So it'd be like this, okay? My fist would be my boron atom, and my 3 single bonds right here, 3 electron densities. The caps will be the hydrogen atom. So this, okay, in this case, the electron geometry would be the trigonal planar. Okay, so this one will be trigonal planar. Okay, it means triangle plane. Okay, trigonal planar. Now, what about this one? Ammonia, NH3. Okay, let's count the electron densities. 1, 2, 3, 4. We have 4 total electron densities around the nitrogen. So therefore, think about how they can how they can minimize the repulsion with the greatest distance. Okay, so with four electron densities, the electron geometry will be like this. Okay, it's a tetrahedral because this is the orientation that can minimize the repulsion. Okay, so let me write this down. This is going to be the tetrahedral. Okay, now let's look at the water. Okay, for water, it is the same thing. 1, 2, 3, 4 full electron densities, like this. So it's still tetrahedral. All right. Now let's consider this one. Now this one's a little bit more complicated because it has 5 electron densities around the phosphorus. So how do we do that? Well, this is going to be a challenge for me. So 5 electron densities, consider these 5 markers are the same because they are the same single bond between phosphorus and fluorine. Okay, so let's start with the tetrahedral. Okay, like this. Now think about this. Where would be the best position to stake in another electron density, and what will happen after one additional electron density is being introduced to the central atom? Now it doesn't really matter which way to plug it in because they're all equal. Okay, they're all symmetrical on every side. So let's just think about putting one additional electron density at the bottom. So putting an electron density right there. Now the existence of this electron density, okay, right here, it is going to repel this 3 electron densities, pushing them up like this. Okay, pushing them up like this. So what would happen is we have this geometry. Now let me show you around. And now I want you to see what happened for this middle section. Okay, does this seem familiar with you? Okay, hopefully you can relate to this one here. So when we have 5 electron densities, the electron configuration will be a trigonal plane in the middle, and then we have 1 electron density at the top, another one at the bottom. So I want you to use your imagination. Okay, be with me. 1 face, 2 face, 3 faces, another face, another right here, another right there. So what you have is actually 2 pyramids with a base of the triangle. So this is why we call this a trigonal bipyramid. Okay, trigonal bipyramid. Okay, now if we have 6 electron densities, what will happen? Okay, let me get a marker. Now, bear with me. I'm going to use this pen for marker. I know it's kind of different. Now, think about where can I stick the other electron density right here. I think it would be best to do it here. So when I put another electron density right here, it will naturally push these two electron densities away and adjust this. Okay, so what you see is a square planar in the middle, and then we have the two electron densities, one on top, the other one in the bottom. So this is called the octahedral. Okay, the shape with 8 faces. 1, 2, 3, 4, 5, 6, 7, and 8. This is the reason why we call this octahedral. So this is the electron density. Oh, this is the electron geometry. Now, how is this different from molecular geometry? All right. Now, in order to prevent the difficulty that I had in part 1 of the tutorial, I'm going to stop here, okay, for a moment, and I want you to click to the next link, okay, to see the difference between the electron density and the molecular density. So please bear with me.